Okay, um, let's start. In today's lecture, we are going to begin with the solid state. Okay, so until now in our course, we have actually understood how the solid state or has come from a mathematical perspective. Okay, using quantum mechanics as a mathematical tool to define or describe the phenomenon which is going on inside the atomic realm. Okay, so the solid state is also in that domain. So that way uh, we have essentially got an idea about how things are from a mathematical perspective. Remember, if you want to do some real life designs, okay, in VLSI domain, then these mathematical equations are what you are going to use, because that will essentially precisely define the reality which we know. Okay. However, in today's lecture, we are going to understand from a very physical perspective. So um, this is going to be more interesting, I hope. So in our previous lectures, we have already described the concept of basis and lattice in order to get a crystal, right? So what we already know is this. So it's just a periodic array of points in space plus, okay, a set of atoms which are essentially placed at each of these lattice points gives you basically this, okay, and so on, okay. Right. So if you are looking at a crystal, so this is your actual crystal, which is a real entity. Please understand that. A physical entity. This is how crystals will look in real life. This is the basis. I will call it basis because this is a single one. Plural of basis is BASES for the plural. So let's not bother about it right now. So here, this can be an atom or an ion or a molecule, as we all know. So this is also a real entity. Okay. Now, this lattice, which is nothing other than a periodic array of points in space. So this is just an abstraction. Okay, so please understand that lattice, this is an abstraction. So lattice is a man-made concept so that we can understand the, so basically the concept of lattice, the abstraction of a lattice is essentially meant to help us define the properties of the crystal, which are essentially dependent on the periodicity of the periodicity of the locations of the atoms, ions, or which we call bases. And there are certain other properties which are dependent on the basis. Okay, so these usually determine, so I'll put this word usually here, determine the chemical properties. Okay, so this is a revision of what we already know, but this is, and this usually determines all the physical properties. Excuse me. Okay. All right. So that means whenever we are speaking about the mobility of an electron, okay, which is an important parameter in any of the device equations, right? So mobility of an electron, okay, resistivity of an electron, of course, that's related to mobility anyway. So work function, all of these are essentially related to the lattice rather than the basis. Okay. All right. So now what we have to understand is that once we know that this is the crystal and hence this is the lattice, now if we want to study it, we have to have the set of physical laws or the rules or the equations, whatever we are going to write, that should be valid throughout the crystal. Yes or no? Obviously, you cannot say, okay, this Maxwell equation is valid only on the right side of the silicon, not the left side. This is so foolish, idiotic, right? Stupid. So what we will do is, we will in order to study this, we are going to have two things to keep in mind. One is how to represent this direct lattice. So this is the direct lattice I'm speaking about. Okay, direct lattice means the coordinates are x, y, and z. Americans call it z. British people call it z. Anyway, so the direct lattice x, y, z. So direct lattice is in the units of nanometers, as I said. Now, whether it is direct lattice or reciprocal lattice, we will come to understand in after some time. Probably next class is better. So in reciprocal lattice, we will, why is this reciprocal lattice important? Remember, in our previous lecture, we have already seen k is equal to how much? 2 pi n by a, isn't it? We have seen that in our previous lecture on chronic penny model. Remember chronic penny model? I mean, how did we reach out to this equation? That was simply from mathematics, right? So the smallest value of k which you can get is when n is equal to 1. You know, so the unit was nanometer inverse, so length inverse. So essentially, we will call this unit in the form of reciprocal lattice. The physical importance or significance of reciprocal lattice will become clear in our next lecture, because if we want to study, so let's understand this. If we want to understand the physical properties of crystal, we are not going to look into the crystal as a whole. We will look into its lattice only. Okay, that's number one. Number two is that lattice तो है, अब ये direct lattice होगा या reciprocal lattice होगा? Now comes the point. Notice that if it is an direct lattice, the situation will look something like this. Dotted. Okay, so this is your lattice here. Okay, all periodic points throughout the entire, wherever you look, you will essentially find only points. Okay, now it becomes a question of how to study it. One is the concept of reciprocal lattice, which we'll see in our next lecture. And the second thing is that we will basically make our life simpler by, instead of going through this entire like infinite number of points throughout in x, y, z, whatever axis, instead of that, we will try to do is, we will try to use only a small section of this points, where we will essentially study the behavior for that, and we will repeat it throughout the crystal. So how can we do that? We can essentially say, we can club together these many number of atoms and say that, okay, if we have, if we can define the physical laws for this particular box, then we can apply the same box. Okay, so let me just select everything here. We can apply the same box over here as well, essentially meaning that if we go on adding the lattice like this, if we can define whatever is going on within this box, we are essentially able to define whatever is going on throughout the crystal. Okay, now obviously, now the second thing which comes is, okay, so this kind of box, this concept that, okay, we will take only a very small, like let us say 5 or 10 atoms, and we will try to see what is the physics or equations or whatever is going on over there, and then we will basically multiply it million times, not million, billion times also, and essentially get the entire crystal physics. Okay, now the issue is, so why 5 or 10? Somebody will say, okay, 50 or 100. Somebody will say, no, I want a bigger one. In fact, there is a concept called macro cell. If those of you who are into material science, you will essentially learn about macro cells later. Okay, but let's not bother about macro cells as of now. What we will rather consider is that, so this box is what? This box is called a cell. Okay, we can all, in some textbooks, they also call it as a unit cell. Okay, unit stands for 1 unit of our consideration, which is multiplied a billion times, and you essentially get the entire crystal. Now the trouble is, अब यूनिट सेल बनाने के लिए आप कितना एटम्स यूज करोगे? So for that, we will try to do what we will try to do is, instead of taking any such generalized case, we will take the smallest number of atoms which the unit cell can contain, and such that that unit cell will repeat itself throughout infinite number of times and give you the crystal as a whole. So that is called something very interesting. So I'll just, what is that called? Many of you might be knowing. So for example, if we can essentially take a smaller section, so unit cell can be larger too. So for example, I could have had, let us say, sorry, I'll put a red here. So this is also a unit cell. Okay, whereas the smallest unit cell means which will have the smallest whole number of atoms inside it. Okay, that is called a primitive unit cell. So as you can clearly understand, nature doesn't bother about this unit cell and all this primitive unit cell. Nature jaisa kaam karta. What we human beings are doing is, we are essentially trying to simplify the problem. Okay, so let me just use this dotted background here. Okay, so this is a primitive unit cell. So what is a primitive unit cell? It is basically the smallest whole number, or you can call it integral number also, but integer means -1, -2. Obviously, this is full. This is not possible over here. The smallest whole number of atoms in unit cell. ठीक है, समझ में आ गया primitive unit cell और unit cell में अंतर. ठीक है. Okay, so once we have got this, now what we will do is, so I have called here atoms. Rather, we will, to make it generalized, let us call it smallest number of bases. Okay, that means I'm generalizing it for ions, atoms, molecules, whatever is in the bases. Okay, very good. So now what we will do is, what are the different kind of unit cells and all? Instead of starting to draw and do it, let's see a video. Okay, that way it will be easier for you to visualize. So I'll stop sharing here. And I shall share. Okay, I'll just, yeah, Srinivas, please tell me.
Sir, for unit cell should contain only one atom, right, sir? Because the crystal has...
No, not really. Because in fact, even in the primitive unit cell, you will observe that it is possible to have even lesser, even more than one number of atoms. Okay, we will see that concept of packing fraction after some time. Okay, so what you are suggesting is only for a simple cubic cell. Okay, so I mean, in reality, what you will observe is that simple cubic cell is the worst possible crystal. Okay, and those crystals are very, very easy to break. Now, what we will learn is that FCC happens to be like face-centered cubic, and that too an interpenetrated one is one of the stablest form. That is called the diamond structure. Okay, so silicon, and I mean, solid state is a huge, again, it's an ocean of knowledge. We will concentrate only on silicon. So silicon is a diamond structure. So today's lecture and the few lecture hence, we will essentially be studying solid state with the perspective of semiconductors only, that too silicon. Okay, now, so we will understand how or what a diamond structure looks like. So I will come to that. In the interview, sometimes, I mean, usually they don't, but I have seen in IITs many faculties ask this, but it is expected that all of you will be knowing it. So can anybody tell me what is the crystal structure of silicon? You have done it in electronic devices course, or you should have done it. It is, many people spontaneously they will say it's a diamond structure. Diamond structure, okay, but the main technical term will be, they will say FCC, that is face-centered cubic. The problem is that it is not face-centered cubic. It is interpenetrating face-centered cubic. Okay, we will understand that today. So before that, let us look at this, let us watch this video, then this entire concept will become clear. Okay, watch this closely. I'll upload it.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular way. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. A unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. There are three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but
So the audio is not clear.
Excuse me?
The audio is not clear, sir.
Audio is not clear. Oh,
Yeah.
okay.
Video is also getting stuck, sir.
So, is it true for everybody? But I mean,
Yes, sir. Yes, sir. It is
Yes,
true.
sir.
so what to do? Just a second. But I mean, instead of explaining this myself, this approach is much better in the sense like you can directly see the entire animation as a whole. So, just a sec. Let's try it again.
by slicing parts that belong to neighboring cells, we see that the actual cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of A particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles portions. In a simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combined to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and back for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and 1 in the center, which is called P to make it easier to see. With full-size mirrors, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 of 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. A face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. does touch a particle in the face, and those in the face touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on a simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and as you'll see in the next 2 examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides, and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper 1 halides and several other compounds. Cl unit cell. Zinc sulfide adopts.
Okay, now everybody should notice how we are putting 2 FCC structures interpenetrating the lattice such that we get the zinc blend structure, which is nothing other than the diamond structure. The only thing is that you are having 2 different atoms. Okay, so this is the one which we are interested in, that is for silicon structure. Notice that in this demonstration, in this animation video, the narrator is essentially bringing 2 different FCC structures and putting them together.
Sir, the audio is still not clear, sir. Everyone is facing it, sir.
I mean, I'm going to upload this video anyway, so
Okay, sir, fine.
So that
Yes,
you can essentially look into it. I do not know. I restarted once again the video, but still.
Okay, sir, no problem. Fine,
Okay,
sir.
but I will again explain it. So you go through the video; it will become very, very crystal clear in you. Okay.
Okay, sir. Yeah.
So if you are able to see the, in fact, the bandwidth or something is probably not good enough for streaming videos, I guess. So I'm sorry about it. But if you can see I have paused the video. So if you notice, there are yellow atoms and the gray atoms. Okay. So immediately after this, I will show you using some software, and that is a material-based software. So in those material-based software, I will be able to kind of it will help you to visualize the zinc blende structure, this structure itself. And what I'm suggesting is that please keep in mind, the impression that I want to make here is that the black atoms, not the black, the gray atoms which you see over here, the 4 gray atoms, okay, they are part of another FCC which has come about. Look. Okay, please note, this is one FCC structure, okay? This is another one. So they are interpenetrating. One is going inside the other, okay? So if somebody asks you, what is the crystal structure of germanium? You have to tell, the answer is interpenetrating FCC. So this is the concept. We will understand this in much better way in the next few classes.
Center cubic arrays of ions and sulfide ions approach and interpenetrate slightly offset from each other. Each ion becomes surrounded by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in the slightly expanded view of the zinc blend itself.
Excellent. I do not know exactly like whether you have got, did you get any permission from our administration to come back to the campus or come to the campus or something?
No, sir, not yet.
But I will highly recommend that at least for the first 1 year of your, in fact, as I told you in the very beginning itself, you essentially have 1 year before your placements begin. Your placements will begin in around July or August of 2022. Okay, so what I will strongly recommend that you should spend this 1 year in the hostels, study with your friends, make a group study. And once you are on campus, I will be kind of available 24/7. Okay, and I have even applied for a hybrid mode of classes so that once you are back on campus, I'll be able to teach you in big classrooms where these recordings will also be there. BITS has got classrooms, huge lecture halls in which there are video cameras attached to them so that the entire class will be recorded and we are going to upload it also. At the same time, you will be kind of live in the classroom so that, because the problems which you are facing regarding the bandwidth and all, all these issues will be gone. This is the first time I'm hearing about this. In fact, last time also it was even worse, but anyway, okay, this online mode will always be a problem. So based on what we have seen, in case you haven't seen, you can see it later on Google Classroom. I'll share the video anyway. So what we will try to understand now is that if we are keeping the atoms just side by side, the simplest way of packing them, simplest way, but please understand this is definitely not the most efficient way. Okay, this is called the simple SCC or simple cubic cell or lattice. Okay, so what there will be another one just behind it. So basically you are getting a simple cube. You are arranging the atoms like that. Okay, the packing fraction and all that, I am pretty sure all of you already know it. In the next class, I will discuss it within 3-4 minutes. So that's not a thing. So this is a simple cubic cell. Now, if you notice, just as the person who was narrating it, he had rightly pointed out, notice that there is a lot of space here which is wasted. Let me use some other color. The space utilization is the worst in simple qubit. Okay, so what we can do is, suppose we put these atoms slightly more efficient way. So how do we define the efficiency of a lattice packing? We are essentially going to ensure that we can stack in more number of atoms in lesser space. Okay, so what is the more efficient one? We will keep so if, I mean, it is difficult to show it on 3D, which 3D is available on that animation. So when I'm drawing it, the first simple cubic was like that. Okay, as you can see, diamond-like structures, which is a very bad way of putting it. So, okay, let me draw another layer. It will become easier for you to understand. Okay, so you can see the spaces wasted here. So let me draw the spaces. So here, okay, so what we are going to do now is that we will just shift all of them like that. Okay, now as you can clearly see that even with the rough, most rough way of drawing this diagram, even then you can intuitively see, instead of this diamond structure, it has now become a small triangles here. Okay, so if you are trying to find out the primitive unit cell for this happens to be body-centered cubic. Okay, or BCC. This is the SC. Yeah, please tell me.
Sir, the wastage we are talking about, what is the disadvantage of this wastage?
Sorry, what is the disadvantage of?
The space that is wasting in the.
Wasting, see, if there is more space between the atoms, what happens is that atom will be the least stable. So if the atoms are very close, for example, here is an arrangement, the other arrangement is here. Okay, so if the space is more, what will happen? The atoms are more distant from each other, so it will be easier to break the bonds. Simple.
Okay.
Okay. So nature will always, we will see in the next few lectures. Do not miss these lectures, by the way, because we have done a lot of mathematics and essentially kind of, roasted you guys. So now in this in these set of lectures in solid state, we will understand it more from a physical perspective. So this intuitive perspective is good enough for your, good enough means very good for your interviews. Remember, in the interviews, you have to explain, you should try to explain physically, okay, intuitively, because you don't have the time to do all the math. The quantum mechanics part is important for you to, go for higher studies, write a paper, technical communication and all that, okay? So this is very important, because I always believe that physical understanding and mathematical understanding go hand in hand. So first of all, you should have a clear idea about the physical understanding. Mathematics will come later. Okay? आप क्यों ये सब कर रहे हो? That should be very clear. क्यों? The why of things should be very clear rather than the exact mathematics. Okay? So I always emphasize that. All right. So what you have asked is a very, very significant one. So मैं ये कह रहा था, efficient one, trying to reduce the space between the atoms. Whoever asked this question, he did a very, very fantastic one. मतलब क्यों करेंगे? Space कम करके हमारा क्या उखाड़ेंगे? Basically, that is the point. So if the interatomic distance is lower, is less, then what happens? The bonding between the atoms will be even stronger. So those atoms will be very, very, those lattice will be more stable. ठीक है ना? Now, and even more, I mean, even better, for example, in this case, this is only a single layer, right? So in this single layer, what we are trying to do is, देखो, this is a 2D level. 2D level पे हम देख रहे थे simple cubic से body centered cubic is better. However, if we are stacking the this is one layer, इसके ऊपर वाला जो layer होगा ना, इस बात को समझना, ठीक है? FCC is difficult to understand, but this is the most efficient one, face-centered cubic. So FCC. तो FCC lattice में हम लोग अभी क्या करेंगे? This is a single layer, so let us copy it as a second layer here. ठीक है? Now in this layer, I shall make it on a different color. अभी हम इसको हम कहाँ बिठाएंगे? अभी ध्यान से समझना. Okay, let me enlarge this so that it becomes clearer to you. This second layer, when I am placing it in the BCC, we will place it just one on top of each other like this. Okay. So in the FCC, what we will do on the other hand, instead of putting it one on top of each other, we will again put it like that. Okay. So that means each of these balls, let us say this, let us even think in terms of an egg crate. Okay. You have seen the eggs crates, right? In the eggs crate, what will happen is the eggs are essentially put. So the red one, you can see here, the red one, let me highlight this, make it larger. So this is the largest one. Okay, so the red one over here is placed exactly at the hole or the spacing between the 3 eggs below it. Are you able to understand? So that means if you're having eggs like that, you're placing the eggs here, not like this. Okay, so that means if you are putting an FCC, you are essentially getting the best packing of space. We can do it mathematically. We will do it in the next class. Very simple. All of you know this, I'm pretty sure, 52%, 76%, and 68%. So anyway, we will look into that. So now, whatever I have shown over here is the packing density, in terms of the packing density. If you are looking into a single cubic cell, so हम अभी क्या करेंगे कि हर एक cell, in all these kind of billiard balls or eggs, whatever, we will essentially now think about how they will look like in coordinate system. So here is an atom. I have exaggerated a lot the space between the atoms. Okay. Then somewhere here, 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 and also this is a simple cubic structure. This is how you will find out the SC. Now, an improvement over this SC in terms of efficiency of the efficiency of the lattice is basically we are going to place another one exactly along in the center of the diagonal. So intersection of the diagonal. So this is one intersection here. The other intersection is here, correct? Opposite diagonal. So here we will have another atom. So I'll erase the intersections. Okay, this is a BCC. Now we'll put the other one. Okay, what is this one? Here we are going to have at the intersection of the phase diagonals. So this was the body diagonal, this was the phase diagonal. So basically these two atoms and these two atoms. So this is basically this phase. So I'll put it here and erase the diagonals. In this phase here and erase the diagonals. ठीक है ना? देखो, this and this atom. So here will be another one. Erase them, and so on. Okay. So this is for the FCC. But remember, is this a structure of silicon? Answer is no. So here I shall add the third one, that is interpenetrating FCC. Interpenetrating FCC. Do not call FCC. I mean, there are FCC. We will see in a minute after this. Interpenetrating FCC is basically this. Control C, Control V here. Okay, and then we are going to bring out this entire section. This is another FCC. This is another FCC. Interpenetrating FCC मतलब इसके अंदर घुसेड़ दो ऐसे, ठीक है? So let's make something more interesting. Okay, let's put it green. I'll put everything as green. ठीक है? And everything here I'll put as blue. Okay, so because I am trying to help you visualize what is going to happen. So this entire FCC, the second one here, is coming and it will settle at a particular offset, small distance between the corner atoms. Okay, now what you get is the interpenetrating FCC or the diamond lattice. Diamond lattice, some people call it diamond zinc sulfide. This is actually zinc sulfide because there are two different atoms I have shown. If they are the same carbon atoms, you essentially get a diamond atom. So zinc sulfide ka standard name is zinc blend. So it's also called zinc blend structure. So if you are speaking about gallium arsenide, for example, gallium and arsenide, two different atoms as the basis, right? So this entire thing will be a basis for gallium arsenide. Okay? Or this is the silicon or usual usual crystal structure for semiconductors. Okay, now we will visualize this using a software. Here. Okay, so here now you will be able to really visualize why silicon is called a diamond structure. Abhi hum dekhenge. So let us open the silicon data file. Okay, you don't have to go into all that. Like those of you over here, if you are pursuing a PhD, then probably you might be interested in understanding all this, or how it is used and all that. These are essentially more to do with the atomistic or DFT, VASP. Okay, there are quantum espresso. There are several such softwares which will do the material modeling. So this is one of them. So anyway, so this is basically the arrangement, and it is basically essentially showing you one cell. Okay, एक unit cell ही दिखा रहा है बस. Okay. Now what I shall do here is that if I do a rotation, you will notice that it is a jungle of all the atoms, right? It is very difficult for you to visualize anything. So here what I will do is I will select those atoms which are outside this square. This is not a square, this is actually a cube, if you notice. ठीक है ना? आपको शायद दिखाई दे रहा है. ठीक है? This is a cube which we are looking at. So what we shall do is we will select those atoms which are outside this cube and delete them. So what I am trying to do is, instead of showing it as a macromolecule or macro cell, we will just concentrate about a single cell, that is a primitive unit cell, so that our understanding is better. Of course, when you are doing the materials modeling, this macro cell or macro structures are helpful, but as of now, for the first introduction to crystallography and crystal structure, I think let's concentrate only on this. Then if we go into the another orientation, okay. So now that we have removed all the extra atoms means atoms which are outside the unit cell. Now what we should do is, if you rotate it, you will find that there are certain atoms which are not having any bond anywhere. देखो, इसका कोई bond नहीं है. The bonded atoms are essentially shown with this. This is essentially called ball and stick diagram in organic chemistry or in chemistry in general. So anyway, no need to bother about that. So we will just remove those atoms which are not connected with the other atoms. Okay. So now this is how your atoms look like. ठीक है. अब एक मजेदार चीज करूंगा मैं. What I shall do is, I shall just convert. I will try to look into it. देखो, अभी क्या है कि I am trying to focus only on the bonds. ठीक है? These are the bonds, right? I am trying to visualize the bonds between the atoms. Instead of that, suppose I want to check in the surface between the atoms, then it is called the polyhedral. Immediately you can clearly see De Beer's diamond has come over here. Remember, this diamond structure which we can now see, that is essentially coming from silicon. The only thing that I have done is this is called diamond polishing. All of you have heard, right? Every diamond ring or every diamond has got a particular structure. So that means the diamond has been polished. Polished means you are removing all the extra atoms. Okay, so that is what I have done in the software. I have simply deleted the atoms which are outside the cell. Okay, everybody. Now if I just rotate it, you can clearly see the diamond structure. But this diamond structure is for what? This is for silicon. I started with the silicon as of now. Okay, so now if I start an animation, you can clearly see, okay, this animation is taking a time here. You can clearly see the diamond structure. Okay, so basically the whole point of this animation and all this thing is that I have done nothing else other than simply cut away the atoms from the like FCC structure, FCC cell of silicon, and it turns out to be a perfect. What are the diamond companies? I don't know. De Beers is one of them. So De Beers ka diamond ban gaya. Okay, so that is the reason why we always compare, like silicon is a diamond structure and all that. Okay, now enough of games. Let us now get back to our standard way of looking into the things, ball and stick. Okay, now what we will try to do. So one thing is clear for us, that the silicon crystal is a diamond lattice. ठीक है, that is interpenetrating FCC. अब यहाँ पे interpenetrating क्यों है? अब देखते हैं. If you notice here, okay, then what I shall do is, yeah, now I'll get back to the original one again, cut away the atoms which are outside the primitive cell. Okay, now, okay, so for the diamond, so the diamond cut, so to speak, I had removed the extra atoms, right? So now what I will do is, I'll keep these atoms and try to visualize the atoms where they are. So notice 1, 2, 3, 4. So if you notice, the ones which I have selected, they are at the corners of the cube, right? So again, on the behind it, so 1, 2, 3, and that one 4. So you can clearly see the 4 atoms at the corners, right? Okay, यहाँ पर अभी ठीक है ना? Everybody with me as of now? I'm trying to show you how they are. Okay, देख लो ध्यान से. ठीक है. Please check this. Visualize it very very nicely because this is going to be a bread and butter. Silicon का ही हम देख रहे हैं. I'm not going into any other element. Okay, so now what we shall do is, once you have seen this, now, oh sorry, I'm sorry, I'm sorry, I should have saved this. Okay, so we have seen the corner atoms. अभी इसमें फेस सेंटर एटम्स कौन कौन से हैं? ठीक है, सिलेक्ट 1, ये फेस सेंटर, इसका फेस सेंटर यहां है, 2, 3, 4, 5 and 6. ठीक है, so now let me, so 1, 2, 3, 4, 5 and what is it, 6. Okay, now if I rotate you can clearly see the face centers. Okay, अभी ये फ्रंट फेस का, अभी ये वाला फ्रंट फेस है, ये फ्रंट फेस है, ऊपर वाला फेस अभी यहाँ फ्रंट फेस हो गया, नीचे वाला यहाँ. ठीक है, these are the 6 face centers. Clear है ना सबको? Everybody? Very nice. Now what we will do is, तो अभी तक हम लोगों ने क्या क्या देख लिया ऑलरेडी? So we have actually selected all the corner atoms, 1, 2, 3, 4, 1, 2, 3, 4. ये corner atoms हो गए. Face centers 1, 2, 3, 4. वहां पर एक है 5 और यहाँ नीचे एक है 6. Now if you notice that if we try to rotate, there are 4 atoms, 1, 2, 3, 4, which are not selected. Yes or no? So the crux of this discussion अभी क्या हुआ है कि we have already selected all the corner atoms and also the face centered. इसके अलावा भी आपके 4 atoms हैं which you can see which are not selected yet. 1, 2, 3, 4. Okay, so these atoms are essentially the result of the interpenetrating FCC. दूसरा जो FCC मैंने दिखाया ना वो वाला. ठीक है, समझ में आ रहा है सबको? Like, very good. In fact, there are 3D models also. If there had been physical classes, I could have shown it through 3D models. But online, unfortunately, we can't help it right now. Okay, अभी हम लोग क्या करेंगे? देखो. So R S. Okay. So now what we will do is this. तो अभी वो फेस सेंटर क्या कहते हैं? सॉरी, फेस सेंटर देखे हैं, कॉर्नर देखे हैं. These are called the, let us say, इंटरपेनिट्रेटिंग वाला या ऑफसेट एटम्स. ऑफसेट एटम्स कहाँ कहाँ होगा? यहां पर एक है. So let us select those. 1, this is 1, this one is 2, this one is 3, and that one is 4. Okay, so now let us rotate and see. देखो, समझ में आ रहा है? देखो, यहाँ पर एक बीच में है, ये तो हो गया फेस सेंटर, यहाँ है एक फेस सेंटर, यहाँ एक फेस सेंटर और ये कॉर्नर. तो दैट मीन्स ईच ऑफ दिस इंटरपेनिट्रेटिंग एफसीसी वाला जो एटम्स हैं, यानी कि जो ऑफसेट वाला एटम्स है ना, सो दे आर ऑलवेज कनेक्टेड टू द नियरेस्ट 3 फेस सेंटर्स एंड नियरेस्ट कॉर्नर. ठीक है, ये हो गया इसके लिए. अब इसका देखते हैं. This is one again offset atom. This is one face center. This is one face center. This is one face center, and this one is the corner. ऊपर वाला देखो, यहाँ एक face center है, यहाँ एक फेस सेंटर है, वहां एक फेस सेंटर है, और ये वहां है, ये वाला है कॉर्नर. तो दिस इज अनदर offset. Okay, the same thing here. Face center, face center, face center, and this is the corner. Okay, clear? Okay, excellent. Now what we shall do is, last thing for today's understanding, time bhi ho raha hai ki just to keep things in perspective, let us highlight the, let us, इसको नहीं, चलो इसको करते हैं. Let us highlight this offset one. ठीक है? Okay, this offset. This offset. So this is one face center, this is another face center, this is another face center, and this is the nearest corner. Okay? ठीक है ना? इसको, or else why shouldn't I do this? Yeah, this is a good idea. एक काम करते हैं, बाहर वाले सारे एटम्स को हटाते हैं. Oh, sorry. यार अंडू नहीं हो रहा है. यहाँ पर एक एटम रहना चाहिए था. चलो यहाँ पर और एक एटम है, मान लो. ठीक है? Now this is our offset one. Okay, so what I'm interested to know is this. Once we have this one, and we will press D, and we will try to find the distance, the smallest distance between the nearest atoms. Now here is the calculation. This is how much? यहाँ पर देख लो, नीचे मैंने लिखा है. It's, of course, it's very small. 2.35 156 angstrom unit. Okay, so I'll put here. Okay, this is angstrom unit, 2.35 156. Okay, now, so here, if we are trying to find out interatomic distance वगैरह, अच्छा, कौन कहेगा सिलिकॉन का, व्हाट इज द लैटिस कांस्टेंट ऑफ सिलिकॉन? Lattice constant of silicon is basically the distance between the corner atoms, correct? तो यहाँ पर फिर से D and D. So the distance between these two atoms is given over here. Just a second. Is see the distance. Yeah. If you notice here, this is hardly visible. It basically writes I've just copied from there. It says length between the silicon atoms is 5.43 angstrom. Okay. Now remember what we found out between the interpenetrating one. It was 2.35156. Okay. So what we shall do here is the distance between the nearest atom was this much, and 5.4307. This is the distance between these two atoms. I want to find out the nearest neighbor distance in silicon atom is this one. Okay, so this is the lattice constant, 5.43 angstrom. This is the distance between the atoms. So if we want to do that, we will just simply divide by 4, and then I'll multiply it by square root of 3. You are left with 2.35156. Okay, as you can clearly see. So what does it, how did we get that root over 3 by 4 is something we will check into the lattice geometry in our next lecture. And furthermore, what I want to show is, the point I want to make is, the second interpenetrating FCC is at an offset of A by 4. So that means if A is the lattice constant of silicon, the second lattice FCC lattice is essentially at a distance of, at an offset of this offset atoms. Remember I told you about this offset atom? This offset FCC is at A by 4 distance along the diagonal, principal diagonal of this. We'll look into this in our next lecture. Okay, thank you so much for joining. So I guess everybody is able to